Hello scholars, welcome. We're talking about plate tectonics, going through all the different types of plate tectonic boundaries and wondering, okay, yeah, that all sounds great, but how does that happen? What drives all this movement? And that is a great question, which we'll discuss in our lecture today. So we will look at the mechanism driving plate tectonics, including mantle convection and the processes of ridge push and slab pull. Let's get into it. So the theory of plate tectonics states that the surface of the Earth is covered by large, rigid bodies of rock. And these large bodies of rock, called tectonic plates, move around relative to one another, and where they meet, we have plate tectonic boundaries. There are three types: convergent, divergent, and transform. Now, the movement of these plates is driven by mantle convection. Convection, like in a pot of water, convection is a method of heat transfer. And this is what the mantle does. The center of the Earth, the core, is very hot and it releases heat. And that heat transfers through the mantle and it drives the crust to move along the surface of our Earth. It's a beautiful system, and without plate tectonics, there probably would not be any life, because there wouldn't be oceans and atmosphere, and life wouldn't be here. So let's get into it. Mantle convection. How about we do something like this? Here's Earth's core. The crust is up here on the surface. The core is hot. The mantle is made primarily of a rock type known as peridotite. But this rock type can actually flow very slowly over geologic time. And what happens is that it flows and the heat rises. That heat cools and it moves away from where it rises and it returns. Heat rises and it returns. Now, this process is going to happen over very long periods of time, millions to tens of millions of years. Where this heat rises, excuse me, I apologize for that. Where this heat rises, you can see the general movement here is going to be away. And so what would we expect occurring? What type of plate tectonic boundary right here? Divergent, absolutely. So here we have a divergent plate tectonic boundary, forming new ocean crust at a mid-ocean ridge. Well, the movement of heat that's creating this tectonic force, the tectonic force we could actually call ridge push, the force that propels tectonic plates away from a mid-ocean ridge. So material comes up, it erupts at Earth's surface, it creates new oceanic crust, and it pushes the opposing oceanic continental crust or the opposing tectonic plates in opposite directions. Divergent plate boundary, like this. That's what's happening. But what's happening, right, when I go like this, I'm starting with mantle convection, divergent boundary. Mantle convection, divergent boundary. It's inherent in there. So new material comes up, and what we're experiencing is ridge. It's a little bit messy. Ridge, push. I'll make this a little bit larger over here. Now we're going to move to a convergent boundary where we have oceanic crust. Oop, next slide, please. Oceanic crust subducting underneath continental crust. Now, rocks have weight. If you've ever tried to carry a big rock, whew, they're heavy. That's how come the center of the Earth, the iron nickel core, is solid, because of the overlying weight of the rocks. It's really heavy. So oceanic crust subducts underneath continental crust, and as it descends down into the earth, the weight of that tectonic plate actually pulls the rest of it with it. I like to think of this as sometimes in winter, it gets cold, so I have the winter blanket on my bed. But sometimes I'm too hot, and so I like kind of kick it to the end of the bed, and if enough of the blanket scoots off of the bed, the weight of the blanket will pull the whole blanket off the bed. This is what Earth is doing. Earth has got its winter blanket on, and its winter blanket is falling off the bed, and it's descending onto the floor. Okay, I know it's a stretch, but I love a good metaphor. And so this process of the subducting plate actually pulling the rest of the plate with it is known as slab pull. Gravity is driving this force. Convection is moving the heat. So here we've got an example. I know I drew it so eloquently and so beautifully up here, but let's take a look. Okay. So here's convection, movement of heat in the mantle over long periods through geologic time. This is what the mantle does. We've got upwelling. We have a mid-ocean ridge that's creating new Earth, underwater volcanoes. That new Earth is pushing the opposing plates, the divergent boundary. When we have subduction where continental crust meets oceanic crust, the oceanic crust subducts underneath of the continental crust, and then here we have the slab pull that is helping to pull that oceanic crust into Earth's interior. We can look at it a different way here. The mid-ocean ridge, mantle convection. Hot air rises, hot rock rises, creating a seafloor spreading center. Oceanic plate travels across. Here's the ridge push, pushing this plate in this direction, but also subduction is going to pull that plate along with it, like the blanket falling off of the bed. So these are all working together to drive plate tectonics. Plate tectonics is the movement of tectonic plates on the surface of the Earth. But Earth has a layered internal structure, core, mantle, crust. And the mantle is responsible for moving heat around. And it transfers heat through convection. This is called mantle convection. At divergent boundaries, new Earth is created at a mid-ocean ridge that pushes the older rocks apart from each other. At convergent boundaries, those rocks that have been traveling across the bottom of the ocean meet a continental crust and subduct and actually help to pull the plate with it. The mechanism for plate tectonics is mantle convection through the processes of ridge push and slab pull. Thank you so much, and I'll see you again.